thermal fluid sciences experts. This is Pro Ready Engineer.
Well, hello again. This is Bassam Abdelnabi from Pro Ready Engineer. This is a much shorter video from the very long 2 hours video that I typically post. So if you like it, make sure to like and subscribe, and just consider watching the full video. Thank you and take care. So now let's move. Before talking to you about conservation of energy, I've given you all the bolts and nuts we need for now. I'm going to introduce you to mechanical devices. We need that before we move forward. What are the mechanical and energy conversion devices I want to share with you about? We have the turbines family. We have the compressors, pumps, and fan family. We have the boilers, heaters family. We have the condensers, radiators family. We have the throttling valves, we have the nozzles and diffusers. These are devices that exist in everything around you. Let's see what they are and what they do. Turbines. These are devices, mechanical devices, that harness energy from energized fluids. If you have a fluid that is energized, that have energy, you put a turbine and you extract that energy. What do you mean extract the energy? You put that turbine and you get that spinning shaft we are talking about. And once you get a spinning shaft, somebody is spinning the shaft. The turbine is spinning that shaft for you. You can do a tremendous thing with this. You have seen water turbines before. I've seen a lot of ads on Facebook and on YouTube of units being sold now. They go to a river. They have this set of blades. They put in the river and the river is flowing, so it's spinning. It's connected to a little generator. And then they have generated power. It's a turbine. It's a water turbine, but a micro turbine. It's a very small turbine. But that's the whole concept of turbines. It takes the energy of the flowing river that by itself is not very useful to you, and suddenly makes that something that is actually very useful. That spinning shaft connected to a generator in this case. You see, when we were kids, they used to sell a unit that is that size of, it's about 3 inches long, 3-4 inches long. It's a generator that we used to hook up on our bicycles. Now here's what it had. At the top there was a little wheel, and we would install it such that this little wheel is touching the wheel of your bicycle. So when you pedal and your bicycle spins, that generator spins, and from that generator there were a couple wires coming out going to a light that you hook up at the front of your bicycle, and there you go. As you pedal, you have light that you will never run off. The battery will never go down because it's using a little bit of your pedaling to give you that light that you need. This is how, when we have a spinning shaft, we can change it to electricity. You've seen that concept before of a generator generating electricity when something spins it. In that case, you are spinning it with your foot, right? Well, in this case, water is spinning it for you. Much better than you having to pedal to spin. Hydraulic turbines, you've heard about dams. You've seen many videos, you've seen pictures, these tremendous structures, you've seen them in the movies that have tremendous amount of water behind them. What's going on there? It's a very nice concept. All this tremendous amount of water, we get it through runners, tubes, and as the water comes down, you see how the water, when it comes down from a fall, right? They tell you that if you fall, if the fall is a large fall, there's a very low chance you will survive that. So that tremendous amount of water flowing, we put these spinning wheels in it, and the water hits it and it spins. And there you go. We take it, we hook it up to a generator. We generate electricity. These dams, they have turbines that generate electricity that comes to your home to power your devices. So what is a steam turbine? It's similar to water turbine, but it uses steam at high temperature and pressure to spin a set of blades to generate electricity again, for example. See, the steam comes in, you see these little blades, we call these little blades, right? And it spins, 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 and now you have a rotating shaft. Hook it up to a generator, now you've generated electricity. Steam turbine. Wind turbines, you've seen them. They are, when you are driving on the highway here in the US, or if you are in Europe, you've seen a lot of them. And in many other countries, you've seen them, but many times they are not in crowded city areas. They need to be a little bit outside, and so it depends on where you are. But these devices does the same exact thing. Wind is blowing, right? All right, we're going to make it spin, shaft, generate power. Gas turbines. Gas turbines, they convert the energy of fuel to mechanical motion, like the jet engine, right? And think about it. If I bring you a bottle of fuel, there's a bottle of fuel. I cap it, has natural gas in it. And by itself, this is useless. Like it's sitting, we human beings want to, make use of that, use it for our needs, use it to help us achieve something. Now, that fuel, if you don't believe me that it has energy, a lot of energy in it, you can just open it up and light it up. And it may not be a very pleasant, so please don't do that. A better experiment is go to your barbecue grill that runs on propane and turn the propane on and stand there, hold your ignition system, whatever that is, and you see it's colorless. You don't see the propane coming out, but you probably can smell it, and light it up, and boom, it lights. This is because it has stored energy in it. Now these devices, what they do is they take this energy from the fuel and give you a spinning shaft for you to do something with it. Gas turbines. So there you go. When turbines are used, they are used for two reasons. Either, like I have said, connected to a generator, generate electricity, or actually use it as a prime mover just to spin something. Now, for the fun of it, there was an attempt, I'm not going to go into the details of what, why, and when, but to power a vehicle with a gas turbine. And think about it, that's not primarily generating electricity, right? What we need in this case is, the shaft is coming out, it's spinning your wheels now. And we've transferred this energy to it's a mechanical drive, it's driving something. Another usage, now this was not successful for many reasons. There's no need to discuss that now. You can Google it. Please do your own research on it. But we can use these turbines to spin compressors, for example. See this compressor we were talking about a second ago, like your pump, your fan. This compressor that is used to pump gases. In your home, you have natural gas. To the most part, you may have. Many of us do, at least, let's say. Where is natural gas coming from? Well, the answer is somebody is pumping it through a gas line to your home. How are they pumping it? They have a compressor installed on the line, pumping that gas, giving it that energy it needs to travel and come to your home. These compressors, someone needs to spin them. Now, for sure, we're not going to hire someone to stand there and, do this. It's not feasible, nor will they be able even to do it. It needs a lot of power. But we put a turbine. We get a turbine, hook it up to that compressor, and there you go. It's spinning it, and now it's pumping the thing that needs to. That's called the mechanical drive. Mechanical drive means I'm using this turbine not to generate electricity, but to do something that relates to a mechanical motion, if you will. When we depict these turbines to analyze them, we many times use a simple schematic as down here. So here's the turbine, it's coming in at 1, this is coming out at 2. This is, for example, the hot gases coming in at 1, the steam coming in at 1, and so on, and leaving at 2 after we have extracted this energy, and that's a spinning shaft right there. We've been talking about spinning shaft to give you work. Good. Let's move on. The second set of mechanical devices I want to introduce to you: compressors, fans, and pumps. We lump them together because they do the exact opposite of the turbine. You need to spin them. They take work to pump something. You are sitting at your own home. You don't feel well. It's a bit hot, reasonably hot, and you turn your fan on. So what is it exactly doing? This motor is giving work, is adding work, and then the blades, as they move, they transfer this work and push the air. They are pushing that air. Now, you say, well, if a fan pushes the air, why is it different than a compressor? If you said that the compressor also pushed the gases, very different. Compressors are used when we want to build pressure. You need pressurized air. Now you need a compressor. Fans are not used for that. Fans are used. What do you need a fan for? Do you need a fan for pressure? No. You need a fan for kinetic energy, to just blow the air on you. Now, compressors, we use them to pressurize the air, to have air, or for that purpose, or natural gas, or whatever the gas is. Compressors, they give you energized gases at high pressure. And I will tell you more about kinetic energy and pressure as we proceed more about the compressors. I think there may be, I can tell you a little bit more. The pump is very similar to the compressor. Pump is similar to the compressor, but it pumps incompressible fluids. You have a water pump, a fuel pump, an oil pump. Incompressibles, they get pumped. Let's say we want to take water from the river. In your own home, you get water, you open the tap and the water is flowing. Where is this water coming from? Well, there's a river somewhere, and there's a pump that sucks this water from the river, adds energy to it, and now it's pressurized water. It can flow in a pipe long distances and come to your home. There will be a tank in the middle of that, but that's not our discussion here. But then it comes to your home. That's a pump. Adds energy to the water, in this case a water pump, oil. In your vehicle, you have a gasoline fuel pump. When you switch your ignition key to on but you don't start the car, you hear a humming. That humming is your fuel pump priming and saying, hey, I'm running. This is why actually when your fuel pump goes bad, that's the very first diagnostic you do to know, my car is not starting. What's going on? Trying to start it today. I hear it trying to crank, and everything appears right, but that's not starting. You put it on ignition and you listen, and now that humming you've been listening to for many years is not there. It's not humming. Well, there you go. You need to go and just put in a new fuel pump. This pump takes the gas from the tank, sends it to the engine. These are pumps, what they are made for. Good. So now we know compressors, pumps are found in the same family. They take work to energize fluids. We tend to sketch the compressor this way. Goes in through one, compresses, leaves at two. We pay work for that. We have to pay work for that. You know, there's a reason for the compressor to be plotted this way. And you've probably noticed it's the opposite of the turbine. And I want to share that reason with you. See, compressors, I told you a second ago, are there to increase the pressure of the fluid, air, for example. So let me ask you, if you write down the mass flow rate equation, we all know that m dot is rho VA. If m dot in this device is constant, m dot 1 is equal to m dot 2, right? The mass comes in, mass comes in. That's why you have a compressor. It takes the air, pumps it, gives you the air. No stored mass. I have applied the mass conservation. If m dot is constant, it's equal to rho VA, and for now accept from me that V is constant. And when you take your turbo machinery, I'll probably be one of the things on my list. Again, I told you I'm following a strategic plan of how I am releasing these materials. So there will be something coming in turbo machinery. For now, V is constant, and just accept that for a second. Well, if V is constant and rho times area is constant, if this is increasing density, rho is increasing. We said that we are increasing the pressure of the air, and rho is equals to P over RT. What happens to the density when the pressure goes up? Density goes up for gases. If the rho is coming up as it's increasing in pressure, then the area has to come down. Conceptually, what it means is something, it makes sense. The air was flowing in this area here, right? And we are squeezing it and making it more compact, high pressurized. We are squeezing it. So the area it needs keeps getting smaller, 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 all the way to the smallest at the exit. This is why it's kind of doing that. And the exact opposite of what I said happens in a gas turbine. So this is why we do it the other way around. And for all of you who have that thought right now, I can see that thought in the brains of few of you. About 10% of you probably have that thought. You said, but if this is a hydraulic turbine, rho is constant, then you wouldn't plot it this way. And you are absolutely right. If I'm depicting a hydraulic turbine, there's nothing wrong to do it like that. Just make no mistake. Nobody will tell you, like, hey, you made a mistake right there. Why did you make the turbine? No, it's a schematic. But you would be better, to be honest with you, it will actually communicate your depth of understanding. You will actually plot it like a box. You'll plot like a box and say, this is my turbine. If it is a hydraulic turbine. Because this concept we just discussed goes away, there's something else comes in. And, in the turbo machinery material that I will present, I may touch a little bit on the different types of hydraulic turbines, Pelton wheels, Francis Kaplan, and then you'll know a little bit more about that concept of specific C and things of this nature. Good. Little bit more on the devices. Now, when I introduced energy to you, I said there is the work side of things, spinning shaft, and I completed that. Two families, a family that spin the shaft and a family that needs a shaft to spin. Now there's the family that there's no shaft. It's Q. It works with Q, heat transfer. Or changing energy form. That's what on this screen. So boilers or heaters, what they do, there's no work. In your basement with your boiler, no shaft spinning, none of that. You burn fuel, you heat the water up. That's it, Q. It's just Q. Take the energy of the fuel, change it to a thermal energy. We heat something up. Condenser and radiator is the opposite of that. It's when you want to remove heat, right? Think about your AC. It's removing heat from your home, then a condenser is involved. There's some sort of a condenser is involved. There's some sort of that heat exchanger that cools things down. Well, it's more of called an evaporator, just to beyond what I want to say today, but it's that device that is pulling air from your home, right? Moving a Q. No, your radiator. In your vehicle, you have a radiator. As long as it's not an electric car. At least in that form. A radiator in your car, water is cooling your engine. It's burning fuel and the water is cooling it. And then what happens is this water, we need to cool it down. So we take it to a radiator, it goes in, we pull the heat out. Now we have colder water, we send it back to the engine to cool it back, and it keeps coming back and forth, right? Goes into the radiator to cool down. At some point in future, there will be a video about heat exchangers. We'll tell you more about how this works in practice. What's the radiator? We'll show you some pictures and we'll discuss more about it. If God gives us the opportunity to do that. Third element is the nozzle. Now, nozzles, what they do, it's not Q and it's not work. They change pressure to velocity or enthalpy to velocity. What do you mean? Well, you know what it means. You take your hose and you squeeze at the exit and you get a very large momentum jet because you wanted to send the water all the way very far away, the portion of your garden or whatsoever that you want to send the water through. You did that intentionally to just get high momentum and send the water. What you've done is a nozzle effect. You've changed pressure to velocity. These nozzles, you see the fire hoses for the firefighters. They have that tip that sort of goes like that, and it gives a very high momentum of water that they use to put out fires. You've seen a rocket with this, what we call conversion-diversion nozzles, and they're doing the same thing. They are exchanging enthalpy or pressure to velocity, to give you that high velocity that you need for a reason. The opposite of these are the diffusers. They are the opposite. They convert velocity to enthalpy or pressure. Not as common as the nozzles in our day-to-day life, because they are typically hidden from your eyes. See the compressors. Let's go back to the compressor now. You know how the compressor works? The fans, they spin Now you have kinetic energy. You told me, yes, that's like the fan. You told me that the fan does that. It spins, gives you kinetic energy. And you said the compressor is a bit different. Now let me tell you why the compressor is a bit different. When it spins and you have kinetic energy, I don't want kinetic energy. I want pressure. So right after the spinning part, I put these passages that are a diffuser. It opens up an area, and now the velocity changes to pressure. I change that kinetic energy to pressure. And then I repeat. This is called the compressor stage. Spinning rotor, spinning blades, diffuser. Spin it, change it to pressure. And then repeat. Spin it, change it to pressure. Spin it, change to pressure. Spin it, change to... You have all these stages put together, and there you go. At the exit, you achieve the conditions you need. You get the fluid at the pressure you desire, if you will. Now, it's a very easy concept when I tell you a nozzle increases velocity. Everybody here knows. If m dot is rho AV and area is coming down, then V goes up. And the opposite is true. You have a diffuser. M dot is constant. The mass running through it is constant. So m dot is rho AV, and A is coming up, then V is coming down. So no confusion there about how the velocity is changing to pressure, if you will. And the way you will know it's changing to pressure or enthalpy is when we write down the energy formulation. So bear with me for a second. But what you know right now is the nozzle brings the velocity up, diffuser brings the velocity down. And in a second it will make sense to you that why, when this happens, the opposite happens to your pressure or enthalpy.